It's been a week. Interesting week outside, that's for sure. So today we are going to start talking about section 6.7, which is on kind of physical applications of the integral. And so there are a couple different applications that I assigned problems over. There are certainly more that we could talk about. Any questions that you'd like me to answer? Yes, sir. 39. Okay, let's take a look. So 39, we have a water tank is shaped like an inverted cone with height 6 meters and base radius 1.5 meters. Okay, so we've got this cone. It has a height of 6 meters, and then this radius right here is 1.5 meters. Very good. Then it says, if the tank is full, how much work is required to pump the water to a level of the top of the tank and out of the tank? Okay. So for this, we do need the formula for work, correct? And so our formula for the work required to pump things out of a tank. Well, first of all, we have to kind of decide where to set up our axes, right? We have to decide, what do we want to be our 0 point here? And what do we want to be our, let's say, 6 point? So we could say that this is 0 and this is 6. That's not horrible to do that. We also could say that this is 0 and this is 6. That might make it a little bit more confusing. It really is up to us, though. So for now, let's just say that this is the point 0, y equals 0, and down here is y equals 6. All right, if we do that, then we're basically integrating from 0 to 6, and then what goes inside? Let's not necessarily write everything in yet, but what are the different pieces that need to go inside?
The force function.
1 second, I'm gonna fix this a little bit. Okay, so we need what? They say rho. What's rho? Yeah, the density of water. Then they say G, which is gravity. Then what? Then we have kind of like the area. Like if I was sitting down here at some point y, I might be curious, what's the area of the slice at y? So basically all of that water right there at that slice takes equal work to pump, right? But it takes more work if you're pumping it out of the tank over the side this way. It takes a lot more work to pump water at the bottom than it does to pump the water at the top. Make sense? So all of the water at this level, that all takes the same amount of work to pump. So they're saying, well, how much water is at that level? And the answer is, well, the area at some depth y. And then it's like, and how hard is it to pump that water? Well, that is the distance that that water needs to come out. So it's the distance from the top and so that they call that the distance of y, basically from how far do you need to pump the water, okay? And then all of that dy. So if you think about it, this makes a lot of sense. It's saying all of that water is the same amount of work to pump, and then how far do you have to take it? So how much is there? How far does it need to go? Down here, How much is there? How far does it need to go? And then just add up all of those and you get the total work that it takes. Make sense? Okay, so now let's start filling in the pieces here. They give us the density of water and they give us gravity. We're working in meters here, correct? And so what are those? 737, 9.8, what the book uses. 737, 9.8 will go outside the integral. These are both just constants, they can come out. Then we get integral from 0 to 6. And now we have to start thinking about this a little bit. Okay, so how can I figure out what the area is at a point y? Remember, this is 0, this is 6. The area of this would be what? Well, first of all, just what's the area of a circle? Pi r squared. So really all we need here, the area is going to be pi r squared, pi, but what is r? R in this case is some functional value. So what is this point right here if I'm sitting at y? That's the question. In other words, what is the equation of that line in terms of y? That, because I've drawn my axis kind of weird, pointing down and everything, can be a little bit tricky and it's easy to get yourself messed up. But one thing that you can do that is almost always right is the following. If y is 0, how far do I go out?
1.1.
Yeah, so 1.5, remember, this is an x value, 0 is a y value. That's a point on the line. Does everybody agree? Another point on this line would be if y is 6, what is x? How far out do I go to the side? 0. So here's 2 points that are on the line. And we know that if we know 2 points on a line, I can calculate the line. So let's just do it really quick. We have to remember that it's y equals mx plus b, right? And m is equal to y2 minus y1 over x2 minus x1. So what is that in this case? Y2, let's say, so this is like 6 minus 0 divided by x2 is 0 minus 1.5. So this is equal to 6 divided by negative 1.5, which is otherwise known as what? Yeah, negative 4. Everybody buy that? So that's my slope of the line I'm looking for. And so now I have y equals m, which is negative 4, x plus b. So in other words, when x is 0, what should y be? Oh, I know that already, right? If x is 0, y should be 6. And if in doubt that you got the right line, plug in the points, right? If I plug in 0 for x, I get 6. If I plug in 1.5 for x, I should get 0, and I do. So this is right, but it's not in terms of y. So I need to solve this thing for x. So I get y minus 6 is equal to negative 4x. Now I could divide both sides by negative 4, and I get negative 1/4 y plus 3 over 2 is equal to x. Sound good? Okay, that's what I want. So that's r, right? What did I say I needed to put in here? Pi r squared. Agreed? So I say pi r, which is negative 1/4 y plus 3 over 2 squared, pi r squared. So that is a of y, the area at depth y. Now I need to say, how deep am I at y? And this is where what I chose for where I set my zero really matters. So in this case, where do I want to pump to? I want to pump to 0. So if I'm sitting down here at Y, how far is it to 0? Yeah.
Is it 6 minus 1?
In this case, it's just Y. Because, okay, so if you're sitting right here on this disk, how far are you from the top? Y. So that's how far I have to pump it out of the tank, right? So, and if I'm sitting way down here at 6, how far is it to pump the water up? 6, right? So if I'm at Y, it's Y away. So I just multiply this by Y. That's the d of Y, dy. And that will get the job done. You asked the question, right?
Yeah.
Does that make sense?
Yes.
Okay. Any other questions? Do you want me to keep going, or do you feel good about this? Or there's a part B also, right?
Yeah.
I can keep going, I don't mind, but this integration isn't like, the integration part isn't the hard part, right? This is the hard part, is figuring out what are all the pieces that go in the puzzle. And then integration, these are just like power rule type stuff. Let's look at part B on this problem. It said, so this is number 39, part B. Is it true that it takes half as much work to pump the water out of the tank when it is filled to half of its depth as when it is full? Okay, just a second. Is it true that it takes half as much work to pump the water out of the tank when it is filled to half its depth as when it is full? Oh, okay. So basically what they're saying is do this problem and see what happens, right? And then they said, then do the problem again. But instead of integrating from 0 to 6, what should you integrate from?
3 to 6.
Yeah, from 3 to 6. And then they're saying, is the answer half of the original or not? Any guesses?
No.
Almost certainly not, but maybe it's just like a total luck shot, given that there's a lot more water up here to pump out than down here. But my guess would be absolutely not. But you'd have to work it out to be sure. Sound good? Yes, sir.
Can you number 41?
41. Let's look at it. Yeah. Okay, so 41. We've got this sphere, right, that is being filled. So let's see. There's our sphere. And then we have this little pipe right at the bottom that they tell us is 2 meters tall. And then this is, the radius here is 8 meters. Okay. So it has its lowest point 2 meters above the ground. Okay. It's filled by a pipe that feeds the tank. Okay. Neglecting the volume of the inflow pipe, how much work is required to fill the tank if it's initially empty? Okay. So pumping water into something and pumping water out of something isn't so different, in the sense that if I am sitting down here at height 0, I've got to get a bunch of water up to this height, right? And I've got to get a bunch of water up to this height. And I've got to get some water up to this height, right? So it's basically, I've got to take different amounts of water to different heights. And so I just need to say, okay, what are all the heights? What are all the distances it takes to get to those heights. Let's add all those up and see how much work it is. Okay, so let's look at the work. So this is integral from. Okay, now this is where it matters when we start putting together our integral. Where do we put 0? Whenever I'm working with a sphere, I really, really want 0 to be in the middle of the sphere, because spheres equations are sort of nice to work with in that case. If it's not, it's kind of like a nightmare. So let's just put the origin right here. Okay. And then I could decide whether I want this to be, I think we just want this to be the positive y-axis. So to get to the bottom of the tank is 8 meters, right? And then and they said, just ignore filling the pipe. All right, so in this case, what am I integrating? And this is going to be my origin, so this is 0. So down here is positive 8, we'll call it. So I need to integrate from what to what?
-8.
If you wanted to, like, there's nothing wrong with that, by the way. I just want to be clear. I'm not going to do -8 to 8. I'm going to do 0 to 8. And consider this the point 8. So I'm making this a positive axis going down, just because I like positive numbers. But you could make this -8 and it would just affect the integral a little bit, and that's fine. But let's just leave it like this. I think that this is a little bit easier. So I'm going to integrate from 0 to 8, and then we get our density, our gravity, and then we need to put in the area of a cross section. All right, so if I'm down here at a point Y, then the question is, what's the area of that circle? Well, to know that, I need to know that distance, right? That, because it's going to be pi r squared. What is that distance? I don't know. Well, I kind of do know, but I don't know. If I didn't know what that distance is, what distances do I know? I definitely know this distance, right? What's that? Y. Everybody buy that? That distance is Y. I don't know this one. I do know this one. What's that one? 8, because the radius of this entire sphere is 8. So that's 8. So now I have a right triangle, which I know 2 sides of. So I can figure out what the other side is using what? Pythagorean theorem, right? So I can say that if I called this, let's just call it x for now. I know that x squared plus y squared is 8 squared. I'm trying to figure out what is x. So I get x squared is 8 squared minus y squared, or x is equal to the square root. Normally it would be plus or minus, but I'm pretty sure we're wanting a positive number for x. Is 8 squared, which is 64, minus y squared. Okay, so that's this distance. Now, what is it that I actually wanted to put in there? I wanted to put in the area of that disk. That's pi r squared. So pi times the radius, whatever that is, and we just figured out it's this. So times the radius, square root of 64 minus y squared. squared. So pi r squared. And then I say, okay, I'm sitting down here at y. How far did I have to pump water to get it to y? And we're not pumping from y out of the tank anymore, right? We're pumping water from what number to y? 10, right? It starts at 10 and it has to get to y. So if I'm sitting down here, how far do I have to go to get to y? 10 minus y. Does that make sense to everybody? So 10 would get me to here, minus y would get me to y. So this is times 10 minus y is the distance it needs to be pumped, dy. And that will get the job done. Let me see if I can
show you how much work it takes to fill the bottom half of the sphere?
Did it say the whole sphere?
Yeah.
Oh, boo.
I think so.
Yeah, you're exactly right. For whatever reason in my mind, I was thinking the bottom half of the sphere. How do I adjust it to make it right? Yeah. -8 to 8.
Yeah.
Yes. So all I'd have to do is instead of having 0 to 8, which says fill from here to here, I could go from -8 to 8 because up here is -8. So if I went from -8 to 8, that would get the job done. So you're right. This 0 to 8 fills the bottom half. -8 to 8 should fill the entire thing. And if you're ever in doubt, plug some things in and actually say, does that work out? Like if I plug in -8, then how far should I be from the bottom? Well, 8, 16 plus 2 is 18. If I plug in -8 right here, I get 10 minus -8, which is 18, which is exactly what I want. And I say, if I plug in -8, what should my radius be? It should be 0. So I plug in -8, square it, 64. 64 minus 64 is 0. Squared is 0 times 5, 0. It's perfect. The really nice thing about these problems is it's really easy to test if you set it up right. Just plug in, look at it, and say, okay, at 0, the radius should be 8. So if I plug in 0, do I get 8 for the radius? And I do, right? So if you can kind of think about it a little bit and just say, what are some different things that have to happen? And if I plug them into the formulas I've created, does that happen? If it doesn't, probably something's wrong. Yes, sir.
Could you have just done like from 0 to 8 and then multiplied by 2?
That's a very good question. In this case, no. It's not symmetric. Now, the reason that it's not symmetric is because, like, take the water, let's say that this is like halfway up. So this is at like 4, right? Up here at -4, we get that water that needs pumped in, right? Now, would you agree with me that this water and that water has the same area? If you just cross-section it, it's the same. But did we lift it the same amount? No. So the area part, this part, that's the same for both. But the lifting piece, how far did you have to lift that water, is different. So this water up here is exactly the same water as this water, but this had to be lifted much higher. So this water is going to take a lot more work than the water on the bottom. Make sense? Yeah. Other questions? let's see, somebody said something online. Oh, they said, can you slow down? I can't write this down. Well, slow down a little bit now. Any other questions? Yeah.
I haven't watched the lesson, but does it explain there why that works, or like how it, like, why that formula is what it is?
Yeah, so what is, have you taken physics? Okay, that's fine. Has anybody taken some physics in high school? Okay, does anybody know, just like in general, what is the formula for work? Yeah, it's force times a distance. And so one way of measuring a force is kind of like, okay, you take, basically you're taking a density times the force that's being exerted on that density over an area. So your density over an area is giving you the amount of, I want to say that what is all of this sort of combined? And it's kind of interesting that I stuck the dy in there. Yeah.
Yeah, I mean, I know like the area dy is like volume of a.
Yeah, so the area plus dy is just like a little thin cut, right? So it's saying take a little tiny cut of y and then find the area of that cut over some depth, right? And so that's a volume. Area over a little bit of distance is volume. So you're taking a volume with a density, and then you are saying how much force is on that particular disk that has a certain mass. Then you're saying, okay, now that you know, move that mass over a distance. So basically, this is the formula for work. And so what you're doing is you're saying, take a mass over a distance, right? And so this is the mass part, and this is the distance part. And then it says, but normally when you do this in like physics, it's just like, here's a block. It has mass. You pull it across the desk. You pulled it across the distance. So how much work did you have to do, given that like we ignore friction and all, all these things? Well, okay, this is the same thing except how many different masses do I need to move? In some sense, infinite, right? Because there's all these different masses that have to move different distances. So what the integral allows us to do is says, why don't you just chop them up into a lot of little pieces and move all those pieces, and then if you cut it up into enough pieces, that would be it. Does that kind of make sense?
Yeah.
So this is actually like the big idea of integration, right? Is integration says, here's something that seems hard. Like how much work does it take to empty a pool? It's like, oh, well, it's kind of like varying depths and varying widths, and it's a big fat mess, basically. And what it says is, okay, what if you could just deal with one little cross section of that pool? Could you figure it out then? It's like, oh yeah, I can figure it out then. It's like, and integration says, okay, now just add up all those cross sections. It's like, that's actually pretty cool, right? That's possible. And actually, the computation isn't even that hard at the end of the day. Integration, I mean, maybe it seems a little bit hard when we're doing long problems on the board, but at the end of the day, it's not really that hard, right? In the grand scheme of what you just did. Yes, sir.
Yeah, based on your science, it's a lot easier than not able to do it at all.
Correct. And, if you were to talk to the ancients or something, they would be kind of like, well, That's a really interesting problem, but, and we could kind of take measurements and stuff and kind of try to figure out maybe what kind of work, but to do something exact, it's like, well, you can't. But it's like, well, you can. And it even, we could do it on one board. You know, that's kind of amazing. So, other questions? I'm not working through these because in the grand scheme of things, these are much, much easier integrals than what we were doing before. Just, I think you can make it through the integral. Anything else? Yes, sir.
Maybe do number 45.
45. Okay. Okay, yeah. So it's very similar to the first one we did. So 45. So we have an inverted cone again, 2 meters high, radius of 1/2 a meter. So this is 0.5 meters or 1/2, whatever you like. What did they say? Yeah, they say 1/2, so why not? 1/2 a meter. And then they say that the height is 2 meters. 2 meters. Okay. If the tank is full, how much work is required to pump it out to a level 1 meter above the top of the tank? So most of the problems we've been doing, we just take it out of the top of the tank, but maybe like there's a hose and there's like a bar up here, a meter higher, and then the hose is like running over the top of that bar. So we have to pump it even higher to get it out. So an additional meter needs to be cleared with this water over the top of the tank. So how much work does it take? Okay. So again, the key is we could set this up all sorts of ways. Last time, remember, I set it up where the origin was up here. Why don't I do something different just to be cute and show you we could do it some other way? Okay, so why don't I put, this time I'll put the origin here. This is 0. And this time I'll say that this is the positive y-axis. So right here is going to be 2. And I need to pump it up over 3. This isn't very in scale, is it? If that's 2, 3 would be way up there, sorry. So 3 is more like up here. So we need to pump the water up over 3. Okay. So the work is equal to integral from 0 to 2, because the water, if I was slicing the water, I would start slicing at 0, and I'd keep taking slices until I got to the top of the tank, which is at 2. Then I've got my density, my gravity, and then I have, if I'm sitting at a point y, then what is the area? So again, we're looking at a disk, which is pi r squared. So we just need to know what r is. And r is, I guess, that distance right there. Again, it would be very, very nice to know the equation of this line, but I set it up differently this time. So if I'm setting it 0, what is the radius? 0, or x is 0. So if y is 0, then x is 0. Okay, up here, this is a y value. So if y is 2, then X is what? 1/2. And so now I have 2 points on a line, and so I could find the equation of that line. So we've got that M, the slope of that line is y2 minus y1 over x2 minus x1. So it's 2 divided by 1/2, otherwise known as 4. And then we've got y equals m, which is 4, x plus the y-intercept. So in other words, when's x equal to 0, what is y? Well, 0, right? So it's just y equals 4x. Of course, I don't want the equation in terms of x. I want the equation in terms of y. So I need to solve for x, and I get that x is equal to 1/4 y. Okay, so what is this thing x? That's the radius. And I know that I'm trying to take a cross section. The cross section is the area of a circle. Area of a circle is pi r squared. So in here I need to put pi times r, which is 1/4 y, squared. Okay, so that's my area. And then I'm saying, okay, at y, how far do I need to pump the water that's sitting at y? Well, if I'm sitting at 0, how far do I need to pump it? 3. So if I'm sitting at 0, I need 3. If I'm sitting at 2, I need 1. What will get that done for me? 3 minus y. Let's put that in, and then we'll check it to be sure. So we said if y is 0, how far should I pump it? We said 3, and if I put in 0, I get 3. I said that if I'm sitting at 2, I need to pump it 1. If I plug in a 2, I get 1. This seems good, right? And so that's it. I have my rho, gravity, area, depth that I need to pump it. And that's it. So again, I'll leave it to you to actually do the integration. Other questions? Yes.
For 42,
Yes.
do you also just have like a depth or so like how does that work?
Yeah, so is this just like on part A?
Here's ABC,
Mm-hmm.
but I think A is like
Yeah, A is kind of the main thing. Let's take a look. So on 42, we have some water trough, right? It looks like this. Right, something like that. It's not the prettiest thing I've ever drawn, but you get the idea. Okay, so what is the length of this thing? Was it 3?
yeah.
3 meters. And then the radius at the top here is what? 0.25? Okay. 0.25 meters, or 1/4 a meter, whatever you like. Okay, and then this thing's filled with water, I believe. Is that correct? Completely filled. And so how much work will it take to pump it out? All right, so a cross section in this case, if I take a cross section of water at a continuous depth, like at one depth, what does that cross section look like? It's always a rectangle. Does everybody agree? And that rectangle has a certain width and it has a certain length. So here is one at, let's say that this is my point 0, and then this is y. And so how far would it be to the very bottom of the tank? Point 0.25. Agreed? So the top of the tank, we're going to, this is confusing, so I'm going to erase it. The top of the tank, we're going to call y is 0. The bottom of the tank, I'll call y as 0.25. And I want to know if I'm sitting down at a depth of y, then what is the width of that rectangle and what is the length of that rectangle? So that's the area. And then I also want to know how deep is the rectangle. Okay. So work is equal to, I'm going to integrate from 0 to 0.25 of rho gravity, and then I need the area that I'm pumping out. So the area of that rectangle. Well, one of the pieces is easy, right? We have a length times a width. The easy one is what? The length is 3. And it doesn't matter how deep I am, the length is 3. So we've got length times width in this case, and the length is 3. And then I need to multiply that by the width, which is kind of the width across the top of a semicircle, right? That's interesting. Let's just look at the side of that tank for a second. So it's a semicircle. This is 0. Here's my y-axis. This is 0.25, correct? I want to know if I'm sitting here at y, how far across is it? Well, what I do know, I don't know that. I do know this. What is that distance? That's y. What's this distance? 0.25. And so I can figure out this distance that I'll call x. Now, once I figure out x, that's not good enough, right? X isn't what I'm looking for. I'm actually looking for 2x. Agreed? Okay, so let's figure out what x is, and then whatever that is, we'll double it. Okay, so we get that x squared plus y squared is equal to 0.25 squared. That, I hate decimals. So let's just say it's 1/4 squared. So we've got x squared plus y squared is equal to 1/16. Now I need to solve for x. So I get that x squared is equal to 1/16 minus y squared. And then I get that x is equal to the square root of 1/16 minus y squared. That's x. I don't need x. I need 2x. So what goes in here is a length, 3, times a width, which is 2 x's. So 3 times 2 times the square root of 1/16 minus y squared. Okay, so we've got, this is our area of that rectangle at a depth y. And the last thing that we need here is we just need to know how high do I need to pump the water. So I'm just pumping it out of the tank, right? So if I'm at a depth of y, how far do I need to pump it back out? Just y. Everybody agree with that? So if I'm down y, I just need to pump it up y. So this is y. dy. Sound good? How is this going to be done? Like, once you, this is a constant, this is a constant, constant, all of that can come out of the integral if I want to. And then how will I actually integrate that thing? Yeah, it's just a nice u substitution. So,
Is it really that nice?
what's that?
Is it really that nice?
Yeah, it's really nice. I like it. Yeah, I think it's not that bad. All right, we're about out of time. I think that's a good time to stop. Like I said, next time we will do a little bit more on this section if needed. And then I'll also, I will do a review for the exam. So the exam is going to be either Wednesday or Friday for everybody, depending on, we'll just make sure everybody either gets in to take the test on Wednesday or Friday. So you'll just come one of those 2 days. I'll send it out. If you are one of the ones who watches online on Monday, it really probably would be a pretty good one to look at just because I'll talk about the exam. Okay, so make sure that you do get that information on what's going to be on the exam, how many questions, etc., and who's going to be coming on Wednesday and who's going to be coming on Friday. Have a good day. I'll see you on Monday.